Okay, hello everyone. We, the Fantastic Four, will present a comparative study of different AI algorithms using the classic monkey and banana problem here. So, here's the problem statement. The monkey and banana problem is a classic AI search problem where we imagine a monkey is in a room where the bananas are hanging from the ceiling and the monkey must use the available actions such as move, push box, climb and grab to get the bananas. And here's the objective is to reach the goal state where the monkey has the bananas. And next the objective here is our objective is to implement and compare different AI algorithms for solving this problem. So here we evaluate them based on the depth of the solution and the number of nodes expanded and the execution time included. And here's the algorithm used, and these are the two well-known search strategies. They are breadth first search and A star. Whereas in breadth first search explores all the possible actions level by level and the it guarantees to find the shortest sequence of the moves. And whereas in A star we use a we combine the actual cost so far with the heuristic in this case and the distance to the bananas. This allows the algorithm to intelligently move towards the goal and often make it faster and more efficient. And here is the BFS code. In BFS code, we use a queue to explore nodes level by level. And here how it works in our code. Here we represent the monkey's state as its position, whether it has pushed the box and if it has the bananas. And starting from the initial state, we enqueue all the possible next states. We continue expanding states until we find the goal, that is monkey holding the bananas. And here's the key point is the BFS is guaranteed to find the shortest path, but it may explore many unnecessary states like consuming more memory. And here we run the code. Here I got the BFS done and the results append to the CSV. And next we go to the A star code explanation. In A star, it improves the efficiency by adding the heuristic. So in our code, we use a priority queue, that is like min heap, to always expand the most promising node first. So the priority is based on the function called as f of n is equals to g of n plus h of n, where h of n is the heuristic, that is the distance from the monkey's position to the bananas, and whereas the g of n is the cost so far, that is number of steps taken maybe, and this way the monkey is guided towards the goal faster, avoiding the irrelevant paths. And if the heuristic is good, A star is both optimal and efficient. And here is the code where here we classify the class and here we decide the steps, means the next steps, and here's the heuristic value we define, and here's the function we include, and here's we implement. After implementing we get A star is done, results are appended to the CSV, and the code is, we get the code in monkey and banana performance CSV, and here's the result. See, here's the result. Here we got the, so here after implementing both the BFS and A star in Python, here we get the depth as 4. For BFS we got the depth as 4, and whereas the nodes expanded in the 3 cases are 13 and the time is 0 seconds. It can be like very short, so we consider almost as 0. And in case of A star, also we get the same depth, but number of nodes expanded are very less than BFS, that is 5. And here's the time taken is something 0.002, but as we took only single digit, we get 0.0 here. And here, so here after in implemented we implemented in Python as we saw before. Each algorithm is applied to the same problem configuration, and the performance matrix is stored in monkey banana performance as shown before. And next, the performance matrix. Here in performance matrix we consider depth, nodes expanded, and execution time, whereas in depth we consider how many steps to reach the solution, and whereas in nodes expanded we consider how many states were explored, and in execution time it considers how fast the solution was found. And here are the results already which we discussed, and this is a brief analysis here. And next, here's the comparative analysis. So to summarize, BFS is reliable and guarantees the shortest path, but it is memory intensive. That is, it consumes more memory. And whereas in A star, it balances optimally and efficiency, performing best when the heuristic is well designed. And we conclude that BFS is simple and dependable but not scalable, whereas A star is more efficient and practical for real world problems. So this makes the A star preferable when we care about both speed and resource usage. And here's the future work. In future we may extend this work by applying these algorithms to more complex real world planning problems, and by improving the heuristic for faster convergence, and also by extending the problem to multi-agent or dynamic environments. And thank you for listening. We are happy to take the questions if we can. Thank you.